So you probably remember 4 years ago, the
Yes.
talks are 1 hour, 15 minutes.
Yeah,
So
yeah, yeah. Yeah. And there's no, there's a watch there, okay. Yeah.
Yeah, but we can talk. Don't be shy. Come back. Okay, yeah, I'll come back soon. You need this reference paper. Yeah, thanks. Maybe allow them to escape the case. Maybe, but apparently he allowed them to escape.
Now I'm next to you, so it's
Yeah, sure.
okay. So we can start our afternoon session. We're happy to have Pedro Vieira back. So he was a scientific organizer for TASI 4 years ago. Very, very nice set of talks. And he's back and he's going to tell us about S-matrix Bootstrap.
Okay, thank you very much. Thanks a lot for inviting me to give these lectures here. I'll be discussing S-matrix Bootstrap, which is of course a very old subject that has been revived recently. And I'll be mostly focusing on 2 dimensions, even though I will say a few comments about higher dimensions today and in the 4th lecture and perhaps also in the other ones. But we'll be mostly in 2 dimensions where things are simpler. It's also good for the last week. Everyone is tired and space-time in 2 dimensions. There's time, space, you can draw everything in the blackboard. I think it's okay, right? So this is indeed our space-time. So we have time and we have space. Right? And then we can have a particle which moves with some momentum p mu. Okay? And things are easy to understand what happens in 2 dimensions, right? You have 2 particles, they move against each other, they are going to hit each other. They move away, they are not going to hit each other, right? So it's not that complicated to understand what can happen in 2 dimensions. So how do we parameterize this momenta here, this p mu? Well, there are many ways of parameterizing it. So we can say that I have p mu, that I can say that it has some spatial component that I call p with a vector, but of course this is a number, right? This is just to use the usual notation because this is the space component of the momenta. And then if the particle is on shell, the energy would be square root of m squared plus p squared. So that's a convenient parameterization where you give me the velocity of the particle and the mass, and I know its energy. And there are other very useful parameterizations that we are going to use more commonly than this one. This one I'm not sure I will ever use it. For example, in terms of what's called the hyperbolic rapidity, where I parameterize my momenta as cos theta, the energy as cos theta, and the momentum as sinh theta. And you see that this is nice because energy square minus momentum square is equal to m squared. So it's automatically on shell for any value of theta. And yet another one, if I call e to the theta a, I would write m over 2, and then cosh is exponential plus 1 over exponential, so a plus 1 over a, and sinh is a minus 1 over a. So this a and theta, it's not so different. A is basically e to the theta. Not basically, it's exactly e to the theta. Okay? And these last two variables are particularly nice, because if I boost my particle, boosts amount to simply translating theta, or multiplying a. Okay? So let's suppose I have a scattering amplitude where we batch a bunch of particles. So let's suppose that I have here n particles in the past, and I have here m outgoing particles. So, by the way, what would be the distinction? So in the notation where everyone is incoming, if I put arrows to indicate everyone is incoming, then, as Marcus pointed in the morning, these guys would have negative energy. So, right? So I would write the moment, I would put some signs to indicate they have negative energy if they are outgoing. And what is this? How many variables is this a function of? How many kinematical invariants are there for this process here? Well, you see that we have n plus m, let's call it capital N, right? So we start with n plus m variables. We can say n plus m momenta, or thetas, or a's. They are all the same. So we start with n variables, right? But then we go from n variables to n minus 2 from energy and momentum conservation, and minus 1 because we can boost every one. So say go to the center of mass where theta 1 is 0, where theta 1 is at rest, for example. And therefore, this is an S matrix, which is a function of n minus 3 variables. Okay? So for example, if n is equal to 4, which means 2 particles going into 2 particles, then my S matrix is just an S matrix that just depends on one variable that is common to refer as small s, where what is this small s? This small s is just the moment of, say, particle 1 plus particle 2 square, the same Mandelstam variable that Marcus already wrote in the morning for massless particles. And what's the physical meaning of this s? If I go to the center of mass, where this guy has spatial momentum, which is minus this guy, then these two vectors are just the energy, right? So this is just the center of mass energy of my collision square, right? And it's a function of one variable because there's no angle, because space-time is one dimension, so things scatter, and that's it. There's only the energy of the scattering collision, right? So they scatter and there's no angle to scatter at, right? So fine, because there is no angle. So again, how did we count variables? We said that there is n because it's 1 per on-shell particle, right? So this n is 1 variable per particle that is on-shell. And then minus 3, which are the dimension of the Lorentz group, because I have 2 translations in space and in time, and I have 1 boost, right? So that's how we would do the counting. So it's just n particles minus the symmetries that I can use, which are 3 generators for 3 generators of the Lorentz group, right? So, for example, if we were in 4 dimensions, let's use the same logic. What we would call the S matrix would be a function of how many variables. So to parameterize each particle now, I have a 3 vector, right? So we have 3n, where n is, say, the space component of the momenta, then the energy is fixed, right? And then what's the dimension of the Lorentz group in 4 dimensions? Minus Dimension of the Lorentz group in 4 dimensions? No? 6 plus 4 is better, which is also known as 10. Very good. Right? So in particular, let's check. When n is equal to 4, we get 2 variables, and we say that our S matrix is a function of 2 variables that we would call S and commonly use T. T would be another Lorentz invariant. For example, it could be momentum 1 plus momentum 3 square, where momentum 3 is outgoing. Okay? And why does it make sense to have 2 variables when n is equal to 4? Because now we have the energy and the angle. Right? So we can go to the plane where there is the collision, and then we have the center of mass energy and the angle at which they scatter compared to the line that they scatter at. Right? So what do you expect? What number do you expect, for example, in 3 dimensions? This is 4 dimensions. That's 2 dimensions. How many variables do we expect in 3 dimensions when we scatter? We have the energy, and we still have an angle. Right? We still have enough to have an angle. So this is how you can derive the dimension of the Lorentz group in the 3 dimensions, right? So because you know what the result should be, and you know that in 3 dimensions, so the S matrix should be a function of 2 variables per on-shell particle minus, and if I want to get 2 when n is equal to 4, the dimension of the Lorentz group is 6. And indeed, that's of course correct. Okay? So this would be how many this is the number of variables that the amplitude, Lorentz invariant combinations that the amplitudes would be functions of. Okay? It's a nice exercise to repeat. A nice exercise would be to, instead of using variables and parameterizations, to think more Lorentz invariantly. And think, what are my Mandelstam invariants? My Mandelstam invariants, I can call them S, I, J, like S and T, which would be just Pi plus Pj square. Right? These are my Mandelstam invariants. But then they are not independent, because I have momentum conservation and so on. So it would be nice to start here, apply momentum conservation, plus what are called dimensionality constraints. What are these? Let me say a few words. Dimensionality. Dimensionality constraints are, for example, suppose I make a determinant, right? Let's make a determinant of scalar products, for example, Pi dot Pj, right? Where this determinant is 5 by 5. Right? And let's suppose we are in 4 dimensions. Then this determinant must be 0. Why? Because if we are in 5 dimensions, the momentum P5 is for sure a linear combination of P1, P2, P3, P4. But then it means that that column is a linear combination of the other columns. So we get 0 right away, for example, right? In 4D. And of course you see that this leads to some constraints on the S's, because these are basically S's up to m squares. So it's a nice exercise to repeat this counting and obtain these same numbers, starting in this more Lorentz invariant way. So in the notes that I put in the wiki, you have this guided exercise that you can do this counting there, and of course it gives exactly the same result. You get d minus 1 times n, where d is the dimension, instead of 3, 2, and 1, minus the dimension of the Lorentz group. Okay? So of course it should work, and it works perfectly. Okay. So this is roughly about 1 particle and about how many variables would scattering amplitudes depend on if I have n particles. And now let's start considering some particular scattering processes. By the way, this is the plan for the lecture. So today, as you are seeing, we are mostly doing kinematics. I hope to do some perturbation theory already today. If not, the plan is as it follows. So 2, 3, and 4 take at least 1 lecture, but today I think we can do it in less than 1 lecture. So let's see if we can start doing some perturbation theory already today, but we will see. So let's suppose we start with the simplest possible scattering processes, where I collide particles that have all the same mass, m, 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 and m. Okay? Now, I'm not saying they are the same particle. Maybe they have colors. Maybe it's red, blue, scattering against red, blue. Maybe they are distinguishable, but they have the same mass for now. Okay? So if they have the same mass, then if this guy has some rapidity θ1 and this has rapidity θ2, then the final rapidity in the end, θ1 prime and θ2 prime, for the final two states, I could call it θ3, θ4 as well, but θ1 prime, θ2 prime, is equal, and this is just a consequence of energy and momentum conservation. You just impose that energy and momentum are conserved, and you get two options. Either these guys are equal to the initial ones, θ1, θ2, or θ2, θ1. In other words, as a set, the set is the same. The set of initial momenta is equal to the set of final momenta. Right? So, are these two possibilities different? Yes, if the particles are distinguishable. If they are distinguishable, yes. Otherwise, no. Otherwise, it's the same thing. Right? So if I have a solid particle scattering with a dashed particle, of course, there is a difference. If this is red and blue, of this is not the same as okay. This process, we would say it's a reflection process or it's a backward process. And this one, we would say it's a transmission process or a forward process, right? For obvious reasons, right? We actually call it easy and hard. I don't know why. It's a terrible name, but I think I will confuse myself if I start using forward and so on. Those would be the proper names, but I would call it easy and hard. I like to think of this as easy because if the theory is free, this just goes through. Then it's easy. And what's hard is to bounce back. But you know what the proper names are, right? Things bounce back, they reflect. It's not easy or hard. Okay. Okay, so then these are the two possible final states. And therefore, note something that we can do in 2 dimensions that is a bit unusual if you are used to thinking in higher dimensions. So let's suppose we are constructing our S matrix. Our S matrix means that I have θ1 prime, θ2 prime, θ1, θ2 in the in state, and here θ1 prime, θ2 prime in the out state. Right? So what is this? So this would be my S matrix, right? So this is the S matrix. Right? But what is it? So if the theory is free, and let's suppose that we are in this situation here, namely, let's go to the vicinity of θ1 prime being close to θ1, θ2 prime being close to θ2. Okay? So the momenta are close to this configuration here. They could also be here, and what I'm going to write is one expression, and there is plus symmetrization with θ1 prime and θ2 prime. But we'll ignore one of the delta functions. But the point is that the disconnected part, the identity, is what? It's saying that particle θ1 prime is particle θ2 prime, and particle θ1 prime is particle θ1, and momentum θ2 prime is momentum θ2. That's the disconnected part. Right? And then there is plus I times t, where t is the connected part, the amplitude, right? This is what Marcos in his lectures is describing, or is going to describe. When he computes, for example, the free particle is this t here. That's what we compute in perturbation theory. This guy, as we said, it's a function of one variable. What variable? Well, the center of mass energy of these two guys, S, or because boost shift theta, it's a function of the difference of rapidities theta. So here theta would be defined as θ1 minus θ2. If you compute for particle with θ1, particle with θ2, if you compute S, you find that S is 4m square cos square of theta over 2. It's also in the notes as an exercise. Okay, but it's just trivial. Just construct this momenta, compute S square. Okay? And so we have this particle 1 disconnected goes here, particle 2 disconnected goes here, plus it times a momentum conservation, right? Where I have that p1 mu plus p2 mu minus p1 prime mu minus p2 prime mu equals 0. Right? So that's what we would write in general number of dimensions. I would say that I have some delta functions for the space-like momentum plus a d-dimensional delta function for total momentum conservation. Right? But here in 2 dimensions, total momentum conservation implies the same thing as these delta functions. Right? So we can actually, in 2 dimensions, factor out those delta functions and write the following. So I will continue. Equal sign. I'm continuing here. So we can write that this is delta function of, say, p1 minus p1 prime, delta function p2 minus p2 prime. Actually, I switched from theta's to p's, but it doesn't matter. But the point is that the second delta function is proportional to the first, as we saw, and therefore what multiplies is what we call S of theta, the S matrix that depends on theta, which is 1 plus I t of theta divided by sinh of theta, where this sinh of theta is just a Jacobian. Right? So we have these delta functions. The delta functions have the same support, but this is a 2-dimensional delta function. This is a product of 2 1-dimensional delta functions. So they impose the same thing, but there is a Jacobian, right? It's like delta of x and delta of x squared. Both impose x equal to 0, but I need the factor of 2x. Okay? So again, if you see the notes, you are asked to check carefully that once you write down the delta function explicitly, that the Jacobian comes out to be this sinh of theta. Right? That you can write in terms of S if you want to have this equation. So this is something fun that in 2 dimensions, you see, when we say that S, normally we always say in any number of dimensions, we always say that S, and we put this funny symbol, which is a trick so that we don't discuss delta functions, we put fancy symbols. But what it means is that this 1 is a bunch of disconnected delta functions, and this T is an overall delta function of momentum conservation, and you don't mix both because they have different support. One is disconnected and the other is connected. The total momentum is conserved, but the individual ones are not. In 2 dimensions, it's really an equality of functions. The function S matrix of theta is equal to the number 1 plus the function T of theta. So there is no subtlety here. And which one do we like the most, T or S? Okay? So the answer to this very scientific question is it depends. If you do perturbation theory, it's T. So this T is what you compute in Feynman graphs. So for example, if you have a theory which is phi to the 4 with a lambda, then T is lambda plus loops. Right? This lambda is just the contact interaction. Right? But this S is what we like if you want to say, for example, that the probability of getting 2 particles, producing these 2 particles with this energy theta is exactly the absolute value of S of theta squared. And this probability, because we can produce many things in the final state, of course needs to be smaller or equal than 1. Right? So if you want what measures the probability of producing 2 particles in the final state, well, then you like S. If you want to do perturbation theory, you like T. And if you want to convert one from the other, you have this equation. Okay? Is it clear? Good. So let's just think a little bit. What do we expect? Let's think a little bit about this P of theta. Suppose we have So can you see if I write here? I was told that I should not write in the last one, but I would prefer not to erase. But can you read? Okay? Okay. Let's consider a theory with a single particle of mass m, right? Then what do we expect for that probability of theta if I plot it as function of theta? Well, you see that theta equal to 0, right? Means rapidity equal to 0, means they have the same rapidity, means in the center of mass they are they are stopped, right? They are at rest with respect to each other. And indeed, S, if you compute from, I guess that's why I shouldn't use the bottom, if you compute from here, when theta equal to 0, you get 4m squared. So it's 2m squared, right? So it's all working out. It's just the rest energy of my particles, of course c equal to 1 here, square. And then theta positive, or theta bigger than 0, would mean S bigger than 2m squared. Okay? So what do you expect? You expect that you have your theta, and there is a value theta star, and up to theta star, you expect the probability to be exactly equal to 1, and then to decay. Why? Why and what is this theta star? Exactly. So up to some energy, right? Up to some energy, in this range, let's say that energy is smaller than 3m squared. Then up to this energy, the only available states, the only states which have energy between 2m and 3m are two particle states, right? So this theta star, it's asked to compute. You just equate this S to 9m squared, and you get this theta star. Okay? It's a Mark-Koch of 3/2 or whatever, right? So it's the value where you start producing three particles. When do you expect this to be 16m squared rather than 9m squared? Yeah, for example, if you have some conservation, for example, some Z2 symmetry, right? Some theory where phi, there's symmetry with respect to phi to minus phi. Then you cannot produce three particles from two particles, right? So it's also very common. Sometimes this theta star would correspond to 4 particle square. Okay? That's good. That's right. Yeah. So the last thing I want to say about this process is that notice that these particles, this S, obeys this equation, and you can compute T and you can compute U. What is S, T, and U? S is P1 plus P2 squared, P1 plus P3 squared, P1 plus P4 squared. Okay? We already wrote S and T. U is the one that I did not write. It's P1 plus P4 squared. Now, if theta 1 prime is equal to theta 1 and theta 2 prime is equal to theta 2, U is equal to 0 because their momenta are just the same, so there is no momentum transfer. And T you can compute and you get 4m squared sinh square of theta over 2 with a minus sign. And you see two things. So one, you see that S plus T plus U equal to 4m squared. That's true in any dimension. That's a general thing. It's just momentum conservation implies this known relation, that these variables are not independent, but S plus T plus U equal 4m squared. But you also see something, that these two guys are interchanged when I do theta goes to I pi minus theta. Right? So what is this transformation that flips S and T? What's the physical meaning of this transformation that flips S? I remind you that S is associated to these two momenta. So if I put an arrow, this would be S. And T is associated to these two momenta. So I would put like an arrow and indicate T here. So what's the symmetry that exchanges S and T? Crossing symmetry, right? So this is crossing symmetry. It's this transformation is called crossing, right? When theta goes to this. Okay. And notice that it works nicely, that if I have a particle with rapidity theta, if I put here I pi minus theta, what happens to this cosh? Flip sign, right? So it becomes exactly a negative energy, like we were saying several times, that the outgoing particle would have negative energy. So I send the particle from past to future by doing theta goes to I pi minus theta. And that's why I'm implementing this crossing transformation. Okay? So all is consistent. Okay? Now, what about scattering different types of particles? So let's consider a little bit. It's an instructive game that is way less considered if I now have particles of different mass. So M3, M4, M1, and M2. Can you still read if I write here? Is it okay? Okay, so what do we know now about these kinematics? They are more interesting when I have different masses. Well, I still have that S plus T plus U is equal to the sum of masses, M1 square plus M2 square plus M3 square plus M4 square. That's true, as I said, in any dimension. It's just a consequence of on-shellness and momentum conservation. You just plug the definitions and this is a true relation. Okay? But you get another relation that I wrote here in the blackboard beforehand because it's a bit long. If you are in 2 dimensions. Okay? So if you are in 2 dimensions, you get this extra relation. If you are in 2 dimensions. How can you check this relation? Well, in the notes, you can just copy-paste a piece of Mathematica notebook that you just copy this, replace S, T, and U, Shift-Enter, simplify, and you get 0. Okay? So it's true, because you can check. How would you do it in a more scientific way? How would you do it in a more rigorous way? This is correct. You just, you check. You just plug S, T, and U, you plug in Mathematica, it's true. But okay, someone would have to give you. Well, you do this business that I told you before. You start with a determinant that you know is manifestly 0, right? On the other hand, that determinant, the entries are full of Mandelstam invariants. You expand out the determinant and you get this relation. Okay? So in this case, it would be a 3 by 3 determinant. Why? Because if you have 3 vectors, they are always proportional to each other, the third one. And when you expand out, because you have 3, you have STU, and that's why you get this term with STU. It comes from this 3 by 3 determinant. Okay? So this is the relation. So you see that this one plus this one means 1 variable, right? Because I have S, T, and U, 3 variables, but I have 2 constraints, so in fact it's a function of 1 variable. Okay? So let's try to draw the physical scattering region. Okay? So we want to draw what is the physical scattering region. Okay. This physical scattering region is related to what's called the Mandelstam triangle, which is what I'm going to explain now. Okay. So this physical scattering region, when I'm scattering at some energy, right, in the center of mass, S. What needs to be S in order to be physical? In order to be at a physical energy, what should S be? Can S be 3I? No, right? Okay, so I helped a little bit. So what should S be? Real. That's good. But that's not enough. Positive. That's still not enough. more than the center of mass energy, right? So like there, we start our plot at θ equal to 0 in the probability when we add it, which was 4m squared. So there we start at 4m squared, right? This point here, 0, is 4m squared, right? And what's the physical region now? What's S? What S corresponds to the physical region now? It's S bigger than what? So could it be m1 plus m2 squared? You are in the right direction, but it's not exactly correct. Almost correct. Right? Because you see, you definitely need to be above m1 plus m2 squared, because you need to produce enough energy to produce this state. But what about m3 and m4? You need to have enough energy to produce it as well. So you need to have energy bigger than the maximum of m1 plus m2 squared. You need to have enough energy to produce the initial state and the final state. Right? So you need to have enough energy to produce the biggest of the two. Right? So if you are below one of them, you cannot have enough energy to produce these physical two-particle states. Right? What about from the T-channel point of view? If I think from the T-channel, the same amplitude, I want to reinterpret it from the T-channel. Well, this is in the S-channel, right? So this condition is in the S-channel. In the T-channel, we would just say the same thing, exchanging the masses. T needs to be bigger than m1 plus m3 squared or m2 plus m4 squared. And U bigger than, okay, this is actually left as an exercise in the notes. So you see the exercises are not all very hard, right? So some are doable. Okay. And therefore, there is a nice thing we can draw. We can draw these variables. We can draw like this. S, U, and T. Okay. Where I say that above this line, I'm physical. Above this line in T, I'm physical. And above this line in U, I'm physical. You see that I'm drawing it in the same plane because they are not independent. Right? Because there is a relation between S, T, and U. In other words, in this picture, one axis is S, and the other is roughly U minus T. Okay? And therefore, to be physical, we need to be here if we are in the S channel, here if we are in the T channel, and here if we are in the U channel. Right? Where these lines, where they are, so if this is 0, this A is what we computed there. Right? Now this is not enough, because on top of this condition, we need to be physical. Right? We need to impose this condition here, this two-dimensional constraint. So I should draw what this curve here, what this condition here, becomes in this picture here. So let's call this condition 2D condition. Okay? And when I draw it, I get the following. I get some shape like this. So that condition, that's the 2D condition. 2D condition. It implies something like this that you can draw. This is the generic picture that you get when all masses are different. You get some shape like this. Okay? Now, this part here, we know it's unphysical. Right? I don't care that that condition is physical, that that condition is satisfied, because I am at the energies below the threshold, so for sure I cannot scatter. And so the physical regions are this one and this one, this line here. So this is where I am doing physics here. Right? So this is the physical regions, are these two lines. Okay? How would we think about this in higher dimensions? What about higher dimensions? So what did we, of this, which part is valid in any dimension? This one, right? I need to be above these energies to produce my particles. So the fact that I'm outside this triangle, by the way, this triangle is called the Mandelstam triangle. So the fact that I am outside the Mandelstam triangle is true in any number of dimensions. That's still true, right? But this condition, being in the two-dimensional line, being on this line, is not true. What would I impose instead in higher dimensions? If the process is physical, the energy needs to be bigger than the rest energy of the particles. What else do I need to impose? Remember, I have two variables. One was the energy, and what was the other one? In higher dimensions, what's the process a function of? The energy, and what else? The scattering angle. So what do we need to impose? For this angle, what needs this angle to be? Yeah. In other words, if I compute cosine of the angle, it needs to be between -1 and 1. And what do I get when I impose that cosine of the angle is between -1 and 1? Can someone guess? In this picture, that will be an extra condition. So we need to be outside this triangle, and the cosine needs to be -1 and 1. So if I vary the cosine between -1 and 1, it will paint some region. What will that region be? And the answer is, it's the inside of these regions here. So this shaded region is the region in higher dimensions where if I compute my angle, it's between -1 and 1. And that makes perfect sense because you see, what does it mean to have angle equal theta, 0 or pi? That's two extreme cases that are the ones that I can embed in two dimensions. It's the forward and the backwards, or as we know them, the easy and the hard processes. That in higher dimensions, they are related because in higher dimensions, these two processes are not two different things. I smoothly swap these two particles, no problem, because I have transverse directions. No problem, they are not two different things. But in two dimensions, they are. I cannot smoothly go from one to the other. So in higher dimensions, I can physically go from this one, that would be, say, theta equal to 0, to this one, that would be theta equal to pi. So the boundary of what can happen in higher dimensions is the two dimensions. It's the two extreme cases. It's forward scattering and backward scattering. Okay? So in two dimensions, I have this component and this component, right? And they are these easy and hard components that we would have these two processes. Okay? So those are the kinematics of these Mandelstam triangles. And sometimes these regions simplify. Okay? Sometimes this region simplifies. So this picture here. Okay, now I really need to erase. I think I have no more things here. So this triangle here could simplify. So let's do the simplest case. What do you think it simplifies to if I do all masses equal? So let's set all masses to be the same. What do you think that shape that I drew there becomes? Okay. So now let's set all MA equal to M, right? Well, we can see explicitly. We can go to this relation. And you see that if you set all masses to be the same, this is equal to this is equal to this. So these three lines, this number here is the same number, right? So it becomes S plus T plus U, but that's a constant. So all this is just a constant. This is also a constant. So all this part here becomes a constant. What condition do I get? S times T times U plus a constant equal to 0. But you remember u equal to 0 is physical, so that constant is 0. Okay? So when all masses are equal, the condition reduces to S T U equal to 0. That's three possibilities: S equal to 0, T equal to 0, or U equal to 0. So what happens is that this picture here, let's draw it again, and we had something like this, something like this, and something like this, and then something like this. And what happens is that this triangle inside, these round shapes, become sharper and sharper. So let me draw it here. Let me try to illustrate. So in a different color, they become like this, you see? And this becomes sharper here. And the picture becomes just becomes this line here is physical, this one as well, this one as well, this one as well, this one as well, and this one as well. Okay, you see that all that happened was that this became sharp, and now this is a disconnected component. Okay. And so we now have three processes that are all independent. So I can take u equal to 0 or t equal to 0. They don't talk to each other. U equal to 0 and t equal to 0 would correspond to this or this. This could be t equal to 0, and this could be u equal to 0, right? And I am here. This is s equal to 4m squared. So I am here, and I can have t equal to 0 or u equal to 0. And what is this? This is the easy and the hard component. In one case, I have the easy component. In the other case, the hard component. Okay? Which kinematically they are the same. Let me just mention that there is another nice example where we set m1 equal m3 equal to m2 equal m4 equal to m prime, where the triangle would also degenerate, and now, but it doesn't degenerate as strongly as before. It becomes, let me not do a mistake. Yeah, it becomes like this. So here I have these two processes where actually, let me confirm that I'm saying correct. Okay, I think it should be correct, but I have to think a little bit. And then okay, so this triangle that was here degenerates into this inside of this region, and I have this physical line, this physical line, this one here, this one here, this one here, and this one here. Okay, these are the four physical things. And now there are a few different ones, right? So in this case, they are not all the same. It's not like this that all of them look the same, just up to relabeling, right? So let's see why now we expect a few options. And the reason is because now when I have two masses that are equal in a pairwise way, there are two things we could do. One thing we can do is consider the two particles that have the same mass be in the initial or final state. So we can have particle with mass m, go to M prime, M prime. That's one process, right? Where this would be time. The other process would be particle M goes to particle M, M prime goes to M prime. This is what we'll call the easy one. Okay? Let me emphasize that I'm trying to draw here explicitly such that they are parallel, but not here. Here, let me try to draw it in a way that doesn't try to make them parallel, because indeed, if they have different masses, right? If I collide two things that are very heavy and they produce two light things, they go away faster. But momentum conservation, if m is the one that goes through, then this theta is equal to this theta, right? This rapidity is just equal to this. So this one, that's why it's easy. The kinematics are very easy. Whatever rapidity I have here. And here, theta prime 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 is equal to theta prime prime. So that would be what we would call the easy component or the forward component or the transmission. And yet there is another one, right? There are three options, right? Where it's like what happens when you are hit by a truck, right? The truck continues here, M, and here you are M prime, and phew, right? The truck almost didn't move, and you bounced a lot. That's the hard component, because no one likes to be hit by trucks. It's unpleasant. Right? So this would be the hard component. And in this case, you see it's very different to do the easy or the hard component, even though we are in the same initial state, same time going up. So let's map this to the processes. So here, let's call this A. Let's call this B. Let's call this C. So what do we expect here? So here you see that in this S channel, I have two options, this one and this one, that look the same. That's A. Okay? It's the same, doesn't matter. The final particles have the same mass, so I can swap them. Okay? So it means that I'm actually using the notation M1 equal M2 equal M, M3 equal M4 equal M prime in the previous notation. So this is A, and so is this one. This one is also A. Right? Because I swap the two final particles, say, and it's the same process. Then there is one process here, which is the easy one, where just I have zero momentum transfer, like u equal to 0. It's a straight line, just like in the previous case. So then it's here. So this process is B, and this line here is also B, just swapping all m's and m primes. And then I have this one that would be C and C. Okay? And let's see. So this line is the analytic continuation of this line. I can go from this line to this line. It's a straight line. It's easy to analytically continue. Right? What is this analytic continuation that sends me from this side to this side? From one channel to another channel? That's crossing symmetry. Let's look at the picture. Indeed, look at this picture from above. And from the side, you get the same thing. It's just a particle, M prime, swapping. And you get the same thing if you see it from this side or from this side. So indeed, under crossing, B goes to B. Under crossing. Right? What about A and C? If you look at A from this channel, what's the difference between looking, what about looking it from here? Looking it from here looks like that process there. So A and C are related by crossing. And indeed, they are two parabolas here that are the same function. It's two branches of the same function. I can indeed go from this to this, but I have to go through the complex plane. Okay? So indeed, C and A, they are related by crossing. Okay, so if you write down explicit expressions for this S, T, and U, it's a fun exercise to take the masses very large, like if it was a truck against a person and so on, and see that one doesn't change, the other changes, and you can do all that. It's in the notes if you want to have some fun with this kinematics, but for what we are going to do, it's enough. And the last thing I want to do as kinematics, we are going to use all these kinematics Actually, this one with 2 particles, I'm not going to use a lot of it, just a little bit. But I'm going to use the one I'm going to introduce now next time. We are going to start with this. So, yeah. So all this that we have described up to now was for 2-to-2 scattering. And I want to just introduce one kinematical regime which is quite useful that we will use next time to study multi-particle scattering, which was something that actually we introduced with Barak here in the audience and others, which is what I'm going to call a multi-regi kinematics. So this is relevant, and I have to study 2 particles going into n particles. Yeah? Is regi misspelled? Probably. No? That's not a joke. Yeah, because it's random for me. I know it has 2 G's or 2 E's, or maybe 1 G and 2 E's, and each time I pick at random, like 2 coins, and I choose. Sorry?
Do you know how hard it is for me to order the vowels in Vieira?
Yeah, that yeah. So I'm sympathetic, yeah. Okay. So regi, okay, today we got this regi, tomorrow it will be 2 E's, just so that one of them is right. It has 2 E's?
It already has 2 E's.
You mean 3, yeah, okay. yeah. 3 E's. I write 2 E's at the end. I never write 2 E's in the beginning, actually. It's so it's the obvious one, this one, I see. So here is the limit we want to consider. So we will have 2 to n, actually no, 2 to n minus 2, so there are in total n particles, but n is bigger, this n is going to be bigger than 4. We are not considering a 2-to-2 process now. So let me describe it in a picture, and then let's put it in formulas. So I want the following. I want a particle at rest, and then comes a very energetic particle that bashes against this particle that is at rest. And it will produce a shower of very energetic particles that will be like this. One will be almost as energetic as this one. Another one a little bit slower, a little bit slower, a little bit slower. And there is a cascade. And then one is almost at rest. Okay? So let's fix this kinematics. Let's try to impose this kinematics. Right? So what's the idea of the game is you fix n minus 2 momenta, and the other 2 you cannot do. It's momentum conservation, right? So what we have the right is to fix n minus 2 of these guys. So let's fix them. Let's say that this one I fix. So here we are using, let's use light cone coordinates. So P is equal to m a 1 over a. So it's exactly this a that I introduced in the beginning. Remember, e to the theta. So I'm not doing cosh and sinh. I'm doing e to the theta, e to the minus theta. Just go to light cone, right? And then let's choose this guy at rest. So let me call this guy P1. So P1 is at rest, so it's M1, 1. That's my choice. And these guys here, I will choose, I will not fix this one or this one. So these 2 guys, they will be unfixed. Unfixed, I mean, they are not fixed by me. They are fixed by momentum conservation. I'll fix the other ones, and then we'll see what these guys are. But I'll fix these ones. I'll fix this guy, P3, to be M x 1 over x. This guy, P4, to be M x square 1 over x square, and so on until this guy, P n minus 1, to be M x to the n minus 2, 1 over x to the n minus 2. And this is what I call P2, and this is Pn. Okay, that's the notation that I'm using. And X is what's high energy, much bigger than 1. Okay? So you see that I have P3 goes very fast to the right, P4 goes faster, and so on up to Pn, which is the fastest one. Right? Particle 1 is at rest. Right? And now I add up, right? And now I have that the sum of all the P plus components is equal to the sum of all P minus components equal to 0, and that fixes P2 equal tac 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 and Pn equal tac tac tac. Right? I wanted to say something before I do this. Yeah, I forgot. Yes? I know what I want to say. And minus 3, sorry. So P1, sorry, P2, then J equals 3 up to n minus 1, yeah. Sorry, n minus 1.
Oh, the angle.
No, it was okay. N minus 3, n minus 3. N minus 3, right? So it's P3 all the way up to Pn minus 1. I remember what I want to do. I want to put some minus signs because some are outgoing. So this P1 I like, but these P's I want to put a minus sign. Okay, so okay, so yeah, okay. And now once you impose this, what do you get? Right, so you fix this configuration and you get this picture here, indeed, that this P is very fast. So this P is approximately equal to, looks like the fastest one, looks like Pn minus 1. Not exactly, you can compute and see what it is, but it's indeed very fast. It's roughly as fast as the fastest one there. And this guy is roughly at rest. So this guy looks like P1. Okay? In the sense that it is 1, 1 plus 1 over x, 1 over x squared, 1 over x cubed, right? So these guys, they obey some quadratic equation, so there are some square roots. But if you then expand at large x, this guy is very energetic, and it starts, the large x expansion starts exactly as Pn minus 1, but then it has corrections. And this one at large x starts exactly at rest plus 1 over x squared, 1 over x cubed. Okay. Now, so this is a one parameter family of amplitudes. This generates a one parameter family M that depends on a single variable x. So it's convenient. Instead of having n minus 3 variables, we have one variable, right? And so it's not the most generic scattering amplitude. It's a very special one where I have this very big energy and this hierarchy, but it's a function of one variable that will give us some analytic control over this guy. And so what happens now? So what happens now physically to what processes contribute in this scattering process? So you see that you have this huge energy, and if I have a particle which is very energetic, it's relatively easy to lose a little bit of energy and shift a little bit. But it's very hard to have huge energy and shift completely by exchanging a particle and then shift completely again. So in this process, what happens is that most processes that I could draw, of all three-level diagrams, for example, if I start doing perturbation theory that I can draw, almost all are projected out. Because almost all diagrams represent processes where I have some huge energetic particles that suddenly have to lose a huge amount of energy, but 1 over p squared, if p squared is huge, is 0. Right? The propagator goes to 0 if I separate two regions that have very different energies. Right? So indeed, here is a nice thing that can happen. So we have two different possibilities. When I have a tree level, so let's suppose now, so you see we are going a little bit into the dynamics now. So let's consider a tree level, right? Tree level means that there are no loops, means that there is a propagator that separates a left part and the right part, right? So I look at the tree, and there is a tree, and there is a propagator that separates the left part from the right part. And this propagator, G, would be a function of alpha, where alpha here, this left part, contains momenta, a set of momenta, P, that I can P index alpha. Means it could be, for example, P1, P3, P5, some set. Okay? So this is a subset of the momenta 1 up to n. And here is why this labeling of momenta that I wrote is clever. The propagator, well, it has dimensions of 1 over m squared, so let's strip out 1 over m squared. And now there are two options for this propagator. The propagator left can be equal to a sequence 1, 2, 3, all the way up to j, or the complement, right? Or the complement. But what matters here is that I have all ordered particles without missing any particle from 1 to j, or the rest else. For example, this is, for example, alpha equal 1, 3, 4, 6. And the alpha bar is the complement. So left is this and the right is the rest. When I have a situation like this, where particles are not ordered, then there is a lot of energy being transferred from the left to the right. You can just add up these momenta. They add up to a very big number. And 1 over p squared plus m squared for the propagator gives 0. And what's nice is that when the left set is all ordered, instead you compute the propagator and you get -1. Okay? So that's, I leave it as an exercise. You just take those momenta and check this statement. That the propagator, this is the propagator, 1 over the total left momenta square plus m square, that it's equal to -1 or 0. And it's -1 if left and right separate all amplitudes. Okay? So this is a big simplification that allows us to simplify a lot our Feynman diagrams for computing these multi-particle processes. Let me give you an example. Suppose I have this tree-level diagram in a two-dimensional field theory. Right? Suppose I have this tree-level diagram. The claim is that this is 0, this diagram. Immediately it goes to 0. Why? Because there is no way if here, imagine I want this propagator not to be 0. Then it means that here I must have 1, 2, or n minus 1n. The first two or the last two. Suppose it's the first two. But then this propagator could be, say, the last two, but then this one, I'm doomed. This one is somewhere in the middle. So immediately, this graph would not be possible for each propagator to separate the first ones from the last ones. Okay? So this diagram would go to 0 in this multi-regi limit. What about this graph, where I have, for example, a quartic vertex, and here another quartic vertex, and here a cubic vertex? Well, this could survive. But it can only survive if here I have, say, particle 1, 2, 3, here 4, and here 5, 6, 7. Only if they are ordered. So the only diagrams that survive are ordered lines. Okay? So this is a big simplification that we will make advantage tomorrow, that only ordered combs because they look like a comb, only ordered combs survive in this multi-regi limit. Okay? This is a big simplification. So let me already as a spoiler tell you why would we care about these multi-particle processes. Because in the space of field theories, there are some field theories that are special. They are called integrable field theories. They are field theories where you cannot produce particles. So suppose I want to look for integrable field theories. I want to look for theories that don't produce particles. But the general 2 to n amplitude is very complicated. So I need some kind of simplification to probe this possible particle production. And here is one. I could say if it cannot produce particles, in particular, it cannot produce particles at high energy. So let's use this high energy multi-regi kinematic regime to greatly simplify my combinatorics. Allow me to identify which vertices in my Lagrangian are compatible with having no particle production, and in this way start identifying some theories that are special within the space of theories. Okay? And that's what we are going to do tomorrow. And I think I'll stop here, 5 minutes ahead of time. Yeah. Okay. I'm good.
I have time for lots of questions. Mr. DeGrand?
Another reason why this is special is that this is what really, really happens in the real world. This is how science physics happens at the LHC. Do you guys use the word multi-peripheral?
No.
No? Do you know what that word is?
No.
We've been giving a 1970 lecture here.
Okay. I don't know if that's a compliment, but I'll pretend it is. Yeah. Okay. Okay.
No, I mean, this ordering is the dominant ordering for multi-particle production.
Yes. No, intuitively it sounded right? Like you have a big energy, it just moves a little bit, moves a little bit. I think this cascade is very intuitive, but yeah, that's right. So I think the counterpart for this, indeed, it's very much related to what you are saying, I think, is that the analog of in higher dimensions, as I will explain, you cannot have no particle production. That's impossible. But the analog thing that you can have is better soft behavior. And so the analog of imposing no particle production could be imposing improved soft behavior. And there I think these kind of limits could be useful, or maybe they are already useful.
More questions? Yep.
Is there any relationship between this multi-regi limit and large N?
No.
All like
Could you repeat that question?
The question is if there is any relation between large N and multi-regi, and the answer is no. I don't think there is any relation. Uh-huh.
So here, the number of Feynman diagrams are not growing very fast.
That's right. It doesn't grow very fast.
So can we safely conclude that we don't see any instantaneous effects here?
So the question is whether we could say that because the number of diagrams grows very slowly, whether we could say that the expansion will become more convergent than usual. And so note a couple of things. So one is that we are doing, in this exercise that I'm doing here, I'm doing a 3-level computation, right? Normally, instantons is about how do diagrams grow when I stay with a fixed number of particles and go to higher and higher loops. And I'm not saying anything about that.
Let's thank Pedro.
Can I ask you a quick question?
Mm-hmm.
Maybe I just missed this, but what was the definition between left and right exactly?
No, this is just I have a 3-level diagram that separates. In this picture, for example, if I have this dashed line, this is left and this is right.
Okay.
This is the momenta on the right, momenta on the left. So this is the sum of all the momenta to the left of this line. All the momenta to the right is the same.
Okay.
But the left is minus p right.
Okay. Thanks.
Okay.
It's very nice.
Oh, thank you. Thank you.